Okay, let's jump right into this. In today's explainer, we're diving into something that could literally rewrite the rules of how we do science. Look, we all know AI is absolutely incredible at optimizing within a given set of rules, right? It generates answers, predicts protein structures, writes code, all with just astonishing speed. But what if it could do more? What if, instead of just playing the game perfectly, it could actually invent an entirely new game? Today we're exploring self-revising discovery systems and how AI might soon be creating completely new scientific vocabularies from scratch.
Here's a quick roadmap of what we're covering today. First up, AI's next big hurdle. Then, we'll look at search versus true discovery, the math behind paradigm shifts, a fascinating case study on breaking proteins, the MDL gatekeeper, and finally, building self-revising AI. So let's get into it.
Section 1. AI's next big hurdle, the limit of current AI. The big takeaway here is that right now, our existing foundation models are brilliant, sure, but they are completely stuck inside a fixed scientific vocabulary.
Moving on to Section 2, Search versus True Discovery, redefining the goal. This is all about the fundamental difference between playing an existing game perfectly and inventing a completely new one when those old rules just don't apply anymore. To really wrap our heads around this, let's break down 3 specific operations an AI can perform. First up is retrieval. Now, in the context of a scientific AI system, retrieval is simply pulling up an artifact that already exists inside the current scientific vocabulary. Think of it like finding a known landmark on a map that's already been fully drawn out. It's super useful, obviously, but it isn't generating new science.
Next, we have search. So, search is about finding a new path or a new object, but you're still strictly operating inside a fixed schema or vocabulary. If retrieval is spotting that landmark, search is calculating a slightly faster route to get there. You're actively exploring, for sure, but you are still strictly boxed in by the exact same map and the exact same set of rules.
And then we have discovery. This is the big one, the massive paradigm-shifting leap. Discovery means changing the representational regime itself. It's about introducing a completely new effective type, operation, tool, or verifier that literally did not exist in the system before. When the old rules fail to explain the evidence, discovery is the act of drawing an entirely new map.
And this brilliantly illustrates that structural progression. Retrieval just pulls an artifact into the existing schema. Search explores within that same bounded circle. But discovery? Discovery physically enlarges the circle. It transports the old evidence into a totally new regime. It's a structurally different operation that fundamentally changes the vocabulary the AI is even allowed to use.
All right, Section 3, the math of paradigm shifts, the anatomy of an AI system. Because to actually code these philosophical paradigm shifts into a machine, researchers use category theory, which is a highly rigorous branch of math, to act as the engineering blueprint. Let's look at the anatomy of an agentic discovery system built on this math. There are 5 core components here. You need a schema of allowed types and operations. You need a population of those actual artifacts, a provenance graph to track the lineage of how everything was made. You need a gate, or a verifier, to judge new additions. But it's that 5th one, the regime update mechanism, that is the absolute key differentiator. That is the categorical mechanism that allows for a verified transition to true discovery when the current schema just isn't cutting it.
And this requires a major shift in how we view AI outputs entirely. A true scientific AI system state isn't just some long conversation transcript or a hidden vector space. It is a growing, strictly auditable record of typed artifacts. Think about it. If we're going to trust an AI that is changing the fundamental rules of science, we have to know exactly how it reached that breakthrough. In this context, auditability isn't just a nice-to-have feature, it is absolutely everything.
Section 4, a case study on breaking proteins, the builder-breaker real-world test. Let's look at a real-world application here, where a breaker AI finds flaws in a model, and a builder AI proposes new rules to fix them. Across 4 discovery iterations, the AI's world model evolves dramatically. So initially, the AI had a really simple rule for protein flexibility, but then it ran into these complex bending proteins like adenylate kinase, where its old rules just failed completely. It couldn't just tweak a number to make it work. It had to fundamentally rewrite its structural law to account for global collective deformations across the entire protein chain.
Which leads us to this incredible core philosophy of the research. A productive failure becomes scientific structure. I love that. A failed prediction on a protein isn't just an error message to be optimized away. In a self-revising system, That failure is the exact evidence pressure needed to force a regime change. It's the very foundation for discovering a brand new scientific rule.
Let's compare what happened during that transition. A traditional, old additive AI model would have just kept bolting on arbitrary variables to chase the data, right? Just creating this messy, overcomplicated formula. But this self-revising AI discovered an entirely new interaction: mode-conditioned compliance. Now, in simple terms, it figured out that local softness only really matters when the entire protein chain moves together. It didn't just add junk variables, it created a totally new, physically meaningful rule.
Section 5, the MDL gatekeeper, pruning complexity. So how does the system know not to just create an endlessly complex formula? Well, enter MDL, or minimum description length. This is the ruthless judge of whether a new rule is actually worth keeping. Now, what's really interesting about this is the striking contrast. As the stress tests got harder, the data volume scaled up nearly 10 times. Yet the model length barely grew at all, increasing by only 1.3 times. This is the proof of parsimonious scaling. The AI is absorbing an order of magnitude more complexity, but it's doing it without just mindlessly tacking on ad hoc terms. And the statistics from the inner search process are just absolutely fascinating. Out of 388 total proposals generated by the builder, only 25 were accepted by the MDL gatekeeper. That is a tiny 6.4% acceptance rate. But more importantly, bare feature additions rarely survived. Instead, it was removals and swaps that drove the breakthroughs. The AI actually succeeded by pruning and compressing data, not by just adding more code. This breakdown of gate selectivity reinforces that exact point perfectly. The model shed complexity and bought better data fits primarily through really smart structural recombination, things like seeds and swaps, and by actively removing useless features. It proves that retraction and compression are literally just as vital to scientific discovery as accumulation is.
Finally, Section 6, Building Self-Revising AI, the Future. Zooming out, we are looking at the absolute next frontier of human-AI collaboration in science. We're moving toward building truly self-revising AI, systems backed by highly auditable, categorical frameworks that don't just fit curves to fixed data sets, but actively and dynamically evolve the underlying scientific theories when they are confronted with the unknown. So, I want to leave you with this thought to ponder. As these categorical, self-revising systems evolve and scale, will tomorrow's AI just be a tool that answers our scientific questions, or will it invent the very vocabulary needed to ask entirely new ones? It's a profound shift in how we approach the future of discovery. Thanks for tuning into this explainer. Keep learning and keep questioning the rules.